we can define the concepts of a global minimum of a function f of x of many variables and also local minimum in the same fashion. So we can take these definitions stated just recently and we simply reverse the order of the inequalities. Now, if we consider a particular problem of optimization, we have to separate two kinds of optimization problems. So we can consider an unconstrained optimization versus constrained. So what's the difference? In unconstrained optimization problems, we deal with a function which we are trying to either maximize or minimize on what set? Usually it's a domain. So for x belonging to U, where U is a set either open or sometimes closed from Rn. And we start our discussion of how these problems are being solved from the unconstrained case, which is considered more simple than constrained optimization. In constrained optimization problems, once again we have a function which we'll call an objective function of the problem, which should be maximized or minimized subject to some constraint or constraints. These constraints take form of either equalities or inequalities or a mixed constraints combining both types, equality constraints and inequality constraints. So for instance, we start considering a case, then there are some constraints in the form of equations or equalities. So we start with unconstrained problems, which is provided here. We need to state and formalize both necessary and sufficiency conditions for a point to be a point of a maximum or a minimum. And we'll be considering a search for local extrema. Extremum is either a maximum or a minimum of a function. What about the global extrema? We'll be considering, but it will be done later. So from now on, we'll be considering just a case of a search for a local extrema. And we'll be using calculus like in a single variable case. So let's suppose that our function f of x, which is defined on some set U, and we'll consider an open set as earlier, but this time it is continuously differentiable, so it belongs to the class C1 of functions. And I'm ready to state a necessary condition for a point to be a local maximum or a local minimum in the form of the theorem. Let x star be a point from the domain of the function then first order derivatives of this function taken at this point equals 0 for all I starting from 1 up to n. This is a theorem which can be easily proven, so let's prove it. I'll provide the proof in case n equals 2. We'll be considering two-dimensional case. Let me draw a graph. So here we have a function whose domain is a set in Cartesian plane. And here we have a point where this function so that will be our domain U. First I decided to choose a rectangle, but I can replace this rectangle with any open set, whatever. Suppose x star, which is a point, is a point of local maximum, to make it concrete. Then, if we fix x2 at the value of x2 star, and we'll be changing x1 within some neighborhood at this point, then we have a function of a single variable only. So this function is a function f of x1, x2 star is fixed. Then, according to the theorem from a single variable calculus, its first order derivative taken with respect to x1, so this derivative should turn 0 at x1 star, and this is exactly condition in the form of a partial derivative with respect to x1, which turns 0. The same true if we fix this time x1 value at x1 star, and we'll be changing x2 only. So that's a kind of a cross here. And the same true for derivative. And that completes the proof of this theorem.